Okay, to check whether an integer is a multiple of 4 using mask and equality operators, is to know that in binary representation, um, a multiple of 4 can be represented as follows. That is 4, it will be 100, whereas 12, it will be 1100. The thing is to realize that all of them in their bit representation form has zeros as their last two bits. And recall that the AND operator looks at two bits and only returns one in the case of 1 and 1, right? And we also know that the AND operator basically returns the number itself. For example, if you are using, uh, if you fix one of the numbers as 1, 1, and we will have the following combinations. That is like 0, 1, and 1, 1. We will again get 0, 1, 10, like 1, 0, and 1, 1. We will get 1, 0, and so forth, and so on. Right? And we realize that the fourth case might be useful to us. And we also know that 1, 1 in decimal form would just be 3. So we can take the last two bits of the given integer x and use it with the AND operator followed by 1, 1, or in decimal form 3, and we check whether this operation returns 0. So like the entire thing, the entire operation can be translated into code as follows. That is x and 3, and we check whether this returns 0. Okay, for the second question, we are again asked to see whether a given integer x is an odd number. So the key to this question again is to kind of realize the defining characteristics of odd and even number in their binary forms. As we can see here for even numbers, we will never have one in their least significant bit. Whereas for odd numbers, we will always have one in their most and least significant bits. So at this point, we can kind of guess that bit shifting might be relevant or useful because given a particular sequence and order of bit shifting operations, we can kind of see that if these defining characteristics of odd and even numbers are kind of preserved or disrupted. So let's consider the following bit shifting operations. That is, we perform left shift by 1 followed by a arithmetic right shift by 1. Okay, so before we start, just recall that a left shift by 1, we pad the least significant bits with 0, whereas for an arithmetic right shift, we use the initial most significant bit and we copy that or we duplicate it into the new most significant bit. Okay, so for 101, if we left shift by 1, we will get like 010, and for 110, if we left shift by 1, we will get 100. Okay, and then we perform arithmetic right shift by 1 on the intermediate results. So for the first, we would get 001, whereas for below, we would get 110. So we can therefore see that for even number, given this particular sequence and order of bit shifting operations, the group representation of an even number is preserved. But this is not the case for odd numbers. So now we have our test equipment or our testing tool. So to translate this particular testing operation into code, it will be as follows. That is, x, we will first left shift by 1 and we use the intermediate outcome to perform right shift by 1. Again, it would be an arithmetic right shift, and then this test whether this is not equal, like this does not equal to the given input itself. Yeah. Okay, for the third question, we are asked to perform some left rotation. And by left rotation, the bitwise operator that might be useful to us will be the shifting operators. Okay, suppose we are given this 32-bit input integer for just an example, and then also we have 3 as our key. Okay, so why don't we start with performing left shift by 3 bits. So using the following number, we know that we lose the first initial 3 bits here, and then the fourth bit would be copied over to the first bit. So we have something like 1, 1, 1, followed by a bunch of like 0 until the last 6 digits, which we will have 1, 1, 1, and the padding zeros at the end. Okay, so as we can see here, this left shift by k bits operation, it helps us to like kind of define or set the higher bits. However, notice that we kind of lost the initial higher bits, right? So the second operation will be to set lost bits from the left shift operation. So the way that we can do this is to right shift logically by 32 minus k bits. In our case, it will be 29 bits. So what we will have, like, we perform this right shift logically by 32 minus k bits on the initial x input. So in our case, we would have an integer that ends with 0, a bunch of zeros, right? And then we would also have 0, 0, 0 as the first 3 digits, but the string of 6 ones would be the fourth digit. We'll start from the fourth digit and ends at the ninth digit. Okay, it will be something like this. Yeah, and then followed by a bunch of zeros in the middle. Okay, so to kind of like preserve the results of these two operations, what we can do now is to use the OR operator. Now recall that the OR operator outputs 0 when you have 2 zeros on both sides of the operator, and it returns 1 for all other cases, right? So we will get something like 1, 1, 1, followed by 6 ones in the meters and a bunch of zeros, and then at the last 6 digits would have that 1, 1, 1, 0, 0, 0 again. Yeah, so here is the entire rotate left operation. So to translate this into code, it would be something like, I'll just like right up here. It would be something like x left shift by 3 or x right shift logically by 22 minus k bits. Yeah, this would be the solution. Okay, so for this question, we are asked to count the number of ones in an integer. So recall that int is represented in 32 bits in Java. And then the main idea of this method is to get the last bit of n and then we perform our check to see if it is equals to 1. Afterwards, we kind of perform logical right shift by 1 on n itself, and then we repeat the above step for all bits in n. Okay, so going to the coding part, we know that we need to return count, which is of type int. So it will be useful to just like first declare a variable called count of type int and assign it to 0 at the very start and then return it at the end. Okay, now for the iteration part, uh, we will be iterating through all 32 bits of the integer. And then at each iteration, we first get the last bit that is n and 1, which will like fetch the very last bit of the integer n for us, and then it will be 0 at all previous bits. Okay, so if last equals to 1, then we increment count by 1, and then to move on to the next bit, we would perform logical right shift by 1 bit on n. Yeah. Okay, for the last sub-question of question 2, you're asked to swap the bits at bit positions A and B for given integer and if they are different. Okay, so first, know that in order to flip bits, the bit operator XOR by 1 will be useful because 0 XOR 1 will return 1, whereas 1 XOR 0 will return, 1 XOR 1 will return 0. So we can kind of see that the bit value is being flipped by this operation. And secondly, to fetch a bit value at position I of a given integer x for comparison, what we can do is that we would use a bit value 1 and then what we can, using a 1, what we can do is that we can left shift it to position I, and then we use this to copy the bit value at position I of x, and then we logical right shift it by I to get that value with a single bit. So that we can just like compare the bit values at positions A and B of that integer by themselves in a single bit without any other previous bits. Okay, and then for node 3, we would only perform swap if we have different values at the different positions, right? And in the context of bits, this means that we would either have 0 versus 1 or 1 versus 0. Okay, so we can start coding now. We know that we will need to return a updated version of integer n with the bits at positions A and B swapped if they are different. So we can just write down that we will return n first. We will need to perform the check to see if we need to swap, if we need to perform the method, right? So in order to check that if we have different values at those positions, we can use a trick and note 2 that is okay. We would shift one levels by a bit, and then we copy the value of x at we copy the value of n at position A, and afterwards we logical by shift it by A so that we can just like get the value at position A by itself in a single bit. Okay, and we see if this is not equal to the bit value at position B. And if the bit values are indeed different, then we can continue on with this swap. So the way that we will swap is that we will flip the bits at position A and then we will flip the bits at position B, because we would, like by node tree, we know that we would only have these two situations of like difference, and flipping as in XOR would work because in both situations would work, we would always end up with a 1. So in either case, like the XOR can help us to flip the bits. So how this will look like is that n will first take some new value after a bit is being flipped. Sorry, this is not correct. There was still need to like shift 1 to the position A and then flip the bit value at position A of n. And afterwards we flip the bit value at position B of n. And then we update the value. Yep, so that's it.